applications, we're talking about the software. You have to build the bare metal software in order to make sure that when the operating system and apps are available, it will actually run on your chip, right? You can't run the full end target software on your design. It's never available at the same time. So we've talked to, I've seen a lot of the code that's written, and there is mountains and mountains of C code that's written bare metal and then thrown away. Right, it's thrown away when the real software comes along. It's not even reused on derivatives. Okay, so we're trying to look at ways we can improve process, improve reuse, improve the whole, if you like, the time to market. Right. So software standards, I think that's been mentioned several times today. More and more IP interface protocols, there's just huge numbers of them. So that obviously is an area where we can provide automation. The complexity of the IPs, I don't know if you saw, about 2 weeks ago, ARM announced a new interconnect for SoCs, their new family. It's a level 3 cache coherent interconnect. This IP is huge, right? Has huge amount of programmability, huge amount of configurability. How do I integrate that into my system and know it's going to perform? Okay, I mean, it's all very well to say I don't need to verify the design, but is my architecture that I'm plugging it into going to be good enough for the application I'm going to run? So those kind of challenges are totally different to the block level IP challenge. We've heard mixed signal and low power, I think, several times today and this week. Obviously, standards, again, are going to help us in some of this. I know a lot of customers are using WReal for modeling of analog to start doing mixed signal. There's still a whole load more can be done on that. I think there's UVMA as well is going to be, at some point, become significant. Debug, we've done some surveys on IP debug and IP test benches. I think 50%, well, it's a bit like we used to say, 70%, the verification is 70% of the, it's a sort of number that's bandied around. It's somewhere between maybe 30 and 60, who knows. But at the system level, at SoC level, this is even more tricky, right? Can you debug your embedded software? And what platform, you know, your hardware, software, what platform you're going to use to do that debug? I think the scary one is, and we're seeing the consequences of this. It seems very much in the market now. You're either a big winner or a big loser, right? It's a tough time to be in business in semiconductors, and shrinking time to money. The number of respins, if you have to do an extra respin or 2 respins, maybe that means you go out of business, right? It's really that serious. So anything you can do to mitigate this, you know, the time to market is going to be a help. So there's kind of 2 trends and 2, I guess, maybe trends or wishes. There is a shift from the idea that you design all your hardware and then you develop all your software to run on it. Right, that takes too long. Right, it's not going to happen. A lot of what we've seen in the virtual platform space is about addressing this problem. And there's more to come in that, I think. Shift from IP creation to SoC integration. Now, that doesn't mean IP creation is not a big challenge, right? It still is, because the IPs you are building are big and complicated and configurable. But it's a piece of a bigger jigsaw. These statistics come from IP verification. One of the things, one of the challenges presented today was, I think it was from Atlantic. I think it was Martin presented the fact that basically there's about 9 languages you're having to deal with in developing your IP. So debugging isn't about system Verilog debug, right? It's debugging is about a test bench in some HVL connected to a DUT, maybe running software. So you have to be able to debug that. It needs to be multi-threaded. It needs to be context-aware. It needs to be consistent across the platforms you're running on. And so, you know, we're going to see, we announced the Incisive Advanced Debug product very recently, and that addresses some of these issues, and there's going to be more to come. The whole debug methodology, I think this is one of the things I've been looking at, and one of the products I'm responsible for is starting to look at performance validation and performance debug, because that's actually just as big a challenge, if not bigger, and it's a SoC level challenge, it's not an IP level challenge. Okay? One of the challenges that I mentioned several times, certainly on Monday, was can we use an agile type development flow? And trying to go from a sort of serial to a parallel development poses questions about agile. You know, in this sort of flow, we've got hardware being developed, bam, you know, you start bringing up all the software. Well, can we do that earlier? Well, somewhat with virtual platforms, we can do some of this, but it kind of implies that there is potential to do sync points in a sort of agile way, do a Scrum type approach. But, you know, this, for a start, requires the hardware guys talk to the software guys, which in some cases is quite challenging, right? One of the first places I worked at, there was a joke going around, you know, why don't the software people look out the window in the morning? It's because then they don't have anything to do in the afternoon, right? That was how hardware guys saw software guys. In some customers I've been to, the software guys are in a different building or a different country, right? So is that going to be a challenge? I think geography, Jeff Barrett from Broadcom mentioned the fact that a lot of these big projects have parts of the development team scattered around time zones in the world, and that is a big problem. We've been working with a big customer recently where just kind of the build and run of their SoC was a massive problem that had opportunities to improve. Now, that sounds like that's not an exciting research project, you might think, but actually the actual mechanics of building your RTL, building your test bench, building your software when you've got 16 cores in this thing and actually getting it up and running on a simulation, it's really complicated. And then you throw into the mix, you've got scattered geographies. We want to be able to do that same build and run in the US where their system's slightly different from, you know, somewhere in India where their system's arranged. So those kind of geography things, sometimes there's unglamorous stuff that can be done to improve this. What I think, you know, the time to market advantage, maybe it's more that the time remains the same, it's just we're actually doing more in the same amount of time. Every generation of chip is more IP, more software, more pressure, and it's always got to be delivered maybe for a Christmas market. You know, I jokingly said to somebody today that Apple are now defining when Christmas starts because they release an iPhone in time for the Christmas market, and you kind of know that Christmas is coming when the new iPhone comes out. It's sad but true. I think it is true. Now, when I talked about reuse, the whole reusable methodology, what do we mean by reuse? There's a whole other dimension of reuse, which is what's the execution platform you're running on? You're not running all your stuff on an SoC in the simulator. Well, we used to, but it's getting more and more difficult to get value out of that. You can start doing software development and download an iPhone emulator and start writing code now, right? But how much can you reuse? What does the debug look like as you step between these? There's obviously a debug aspect for the software, which is completely orthogonal to the debug for the hardware. So how does that look when we start to get to Palladium and FPGA, maybe even post-silicon? What do we put in post-silicon so that if we find a bug here, how do we replicate it here where we can do more debug? That's really important, right? And how do we find, if we find a bug here, can we move it to here where we've got even more capabilities? You know, your VIP will run here with comprehensive protocol checkers, coverage, all sorts of good stuff. It won't necessarily run here, right? So can you jump between these execution engines and do the things you need to do? So this is kind of a summary of the problems we see. What I'm going to do in a minute is kind of show you, paint you a picture of what Cadence's vision is, and some of the things we're already doing, and you can envision maybe where we're going to go with this. So the current state, or the state maybe 2 years ago when we started this, was there are multiple disconnected environments. What do we mean by that? Well, you have a virtual platform with a whole load of models, and then you jump from that to RTL. The software can stay the same. What's the hardware? What's the connection? Is it easy to do that? Do you have consistent debug? There's a Palladium or whatever, the Noche, whatever format you're in here, but you've got to jump from here to here. Is that easy to do? Is it easy to jump forward and backwards? FPGA same, right? So that's one of the big, we see that as a challenge for the SoC integration. If you've not got a smooth flow backwards and forwards across the engines, it's going to fail, right? Or it's going to be much more work to figure out what went on and what went wrong in your FPGA, and then go try and reproduce it in simulation. I've already said we're integrating. There's obviously lots of components, significant time, cost of reintegrating and re-verifying. What a lot of customers also said to us was the cost of derivatives. So a lot of companies make families of products. They don't just make one SoC. They make one, and then they slightly change the implementation. More USB ports, less USB, blah, 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 whatever. They said it costs us almost the same amount in engineering to do the derivative as it did to do the first one. That's clearly crazy, right? Anything an EDA should be looking at is automation to ensure that when you design something, you can do a derivative. Maybe it's half the cost in engineering time to do the derivative. Now, that requires a lot of different pieces to put together. It's not one thing that's going to fix that, right? So, I guess, actually, there's one thing here I should mention as well is software use cases. I think Breaker showed some of that concept and why that type of technology is taking somewhat hold, is that maybe the reuse of tests, the tests maybe need to be in C, right, if you're going to reuse them at the system level. That doesn't mean you do all your verification at the block level in C, but you should have the ability to create tests which can be reused at the integration level. And that's something we've been looking at with another customer. So our vision really is to take these multiple, and Cadence has 4 platforms, the VSP platform, the Incisive, Palladium, and RPP. The idea is really to try and make those more and more look like one engine that you can move between. Now, this is not going to happen overnight, but one of the things, so we did launch what's called a system development suite, which is the unification of these about a year ago. What we're seeing is that there are hybrids in between these, where you maybe want some of it in the virtual, some of your design in the virtual platform, some of it may be in simulation, or some of it may be in hardware acceleration. Let me give you an example. Maybe you're developing a GPU. GPUs typically don't have fast models, don't have TLM. They may have TLM models, maybe not. It's unlikely. You may want to do graphics benchmarks on a GPU, right? That's how people measure GPUs. Well, you could have a virtual, an ARM fast model, for instance, connected up with some of your SoC actually in a Palladium box, maybe the whole GPU, whatever IP. You can boot things like Android this way. Android boots in about 20 seconds. If the processor was inside the box, it'd take you like an hour. So suddenly you've got a huge speed up to get to the point where your benchmark starts. And some of the benchmark will be code and some of it will be GPU. You can actually accelerate this quite nicely. And we think there's going to be a mixture. Obviously, you're going to have some kind of transactors to make that happen that will synthesize on the box. we're targeting getting to unified system debugging. Now, this requires a lot of pieces to be in place, but the starting point is debug your multi-language code at the test bench level in simulation. You want a virtual platform debugger that looks remarkably similar, right? Well, that's available now. Then how do you actually integrate that with debug of software, maybe on the Palladium FPGA? So the idea is that your debug should be similar across all the platforms. There are visibility issues, obviously, and that's why you're trading visibility with performance as you go further to the right. Palladium's got visibility, but it's limited compared to, in terms of checking compared to simulation. You go to FPGA, you get less visibility. System VIP, so we have a massive range of VIP and memory models. We predominantly have these in simulation right now, but we also have accelerated VIP. What we mean by system VIP are different incarnations of VIP to support these different use models. And the idea is that they should be, you should be able to step across the platforms to a certain extent, and there will be a level of reuse that you can use. So having perhaps VIP that's driven by software that you can use for both simulation and acceleration, that's the kind of thing we're talking about. We have things like virtual bridge, so this is where you would say, I'll connect the Ethernet of my host directly into the box. So you can actually now bring real-world Ethernet traffic. So it's the idea of connecting the Palladium into the real world. We already have something similar to this with speed bridges, which is a way of running real-time traffic into the Palladium. So things like HDMI, that kind of thing. One of the products, as I said, I'm responsible for is really starting to look at automating the creation of test benches. So test benches at the SoC level are a nightmare because you've got potentially so many interfaces, and you may want different incarnations of them. If the SoC architecture changes, I'm now going to change my test bench. Well, it's much nicer if you actually automatically generate a test bench, and one of the products I'm responsible for is something called the Interconnect Workbench, which will take IP exact and generate a test bench automatically for interconnect infrastructure. And then we've had a product for a long time. So I think from about 2004, 2005, something like that, we had something called the Incisive Software Extensions. So this allows you to basically connect a UVM test bench to your embedded software and randomize it, so you can get corner case scenarios created by randomizing the software. This is I would say we had this from about 2005. This is going to be extended further to address some of the use case scenario generation that you need for these things. And then finally, as Harry started the presentation this morning, the session this morning, overarching all of this, you need metrics, right? vManager, I think we launched it in about 2004, and we've been extending it ever since to support metrics from functional coverage, code coverage, assertions. We can synthesize synthesize coverage onto Palladium. So all of that metric data and regression data. So this specifically allows you to manage regressions and collect data from your regressions. And that's kind of the whole picture of what we're trying to fill out. It's still a work in progress, but I thought I'd share that with you. Hopefully it was interesting. Thank you.